near the wall, etc., is going to have high static temperature. So, which means that the flow temperature is going to be very high, which will have impact on the flow, on the gaseous properties, as well as on the surface, the solid surface that it comes in contact with. So, a lot of considerations in hypersonic flows are focused at the effects of temperature, and that comes because of the huge difference between static temperature and stagnation temperature. As we know from compressible flow, when Mach number increases, the difference in static and temperature, stagnation temperature varies as the square of Mach number, T into 1 plus gamma minus 1 by 2 m squared is the stagnation temperature. So obviously, when Mach number increases, there will be a huge increase in the resulting stagnation temperature as well. So, needless to say, when you have hypersonic Mach number, particularly in the higher range, the temperature is going to be, the resulting temperature within the flow near the surface, etc., are going to be high. And particularly when you have a shock formation across the flow shock, there will be a deceleration, there will be an increase in static temperature, and there will be also dissipations due to viscous effects. So, frictional effects as well as shock, the impact of shock are the two major causes because which lead to the dissipation of kinetic energy to supersonic to high internal energy, and that's a root cause of high temperature. That is a common problem with the hypersonic flow applications. Now, all the relations that we have considered so far, whether it is in viscous flow or inviscid flows, we have mostly focused on perfect gas assumption. And this is one of the major assumptions that will break or probably cease to exist when, or cease to apply when the flow is, when the temperature is very high. So we Cpt naught is Cp into T plus U squared by 2, which leads to the relation T naught is equal to T into 1 plus gamma minus 1 by 2 m squared, which we always use, right? And that is based on the one-dimensional energy equation. And if we use that, for example, just to highlight the difference or the invalid nature of perfect gas assumption at realistic temperature ranges. So Apollo re-entry, I guess the Mach number was of the order of 32. And at an altitude of 53 kilometer, where the temperature, static temperature is 283, and that's just above the 215 or 211 layer above that. So the and where the temperature keeps increasing. So about 53 kilometer the altitude, the temperature, static atmospheric temperature is about 283, and if you use that 283 as the static temperature, then it means that Apollo at a 32 Mach number, 32.5 Mach number, the above relation T into 1 plus gamma minus 1 by 2 m squared gives a value, a ridiculously high value of 58,128 Kelvin. 58,128 Kelvin. Remember, I mean, it's a huge number, right? But in reality, the stagnation temperature in that case is the flight measure based on flight measurements and estimation. It's around 11,000, 11,600. So look at the difference: 58,000 and 11,000. Okay, and that difference, that is 58,000 based on our perfect gas assumption, or T naught is T into 1 plus gamma minus 1 by 2 m squared relation, whereas the actual temperature is close to 11,000. So this difference is attributed to the invalid nature of perfect gas assumption at that high temperature. And one of the major reason why that is invalid is, as we know, the perfect gas assumption always neglects any intermolecular forces. Molecules are supposed to be or considered to be isolated from each other. So that kind of an assumption is what leads to the perfect gas equation, and that's one thing which sort of breaks at those high values, high levels of temperature. So the validity of perfect gas assumption is limited to low pressures where low pressure in the sense when the pressure is not too high to have too much of too frequent molecular collisions, because puff gas assumption does not account for molecular collisions. Similarly, temperatures should not be too low, like 30 Kelvin, and also the gases are non-reacting. That is, the chemical composition has to be constant. So because we don't account for any species or the change of composition when we apply the perfect gas equation. Okay, so but all these anyway, particular the when you have a re-entry condition, the temperature, because of the high temperature, the chemical reactions start occurring at that we have seen already. That is the at different temperature levels, what happens to the chemical composition. So all these lead to reactions, which in turn results in a reacting flow, and the thermodynamic properties vary significantly in the reacting flow, and even more importantly, the fluid properties mu and K. Mu, the dynamic viscosity; K, the fluid conductivity. Dynamic viscosity related to momentum transfer; K related to heat transfer. All these change with temperature, and the change temperature as well as the composition of the gas. And as a result of all that, Cp and gamma are not constant. That is basically the assumption that is related to perfect calorically perfect gas concept. That is, Cp and gamma are considered to be constant, but they cease to be constant, and they will be varying. So all these are part of the chemical effects which happen in re-entry. In this image, actually, we have seen all these changes already right from beginning. That is 0 to 2500 Kelvin. You don't have chemical reactions. We know at 800 Kelvin, the vibrational excitation may start, but that's not a chemical reaction per se. It's a molecular activity, the increased molecular vibrations. So, but 2000 onwards, the O2 dissociation starts. 2500 etc. It becomes more prominent, and as we know, 4000 Kelvin, the more stronger bond of nitrogen, that also starts breaking. So nitrogen also starts dissociating, and then going beyond that, 9000 Kelvin etc., the N2 dissociation completes, and what you have then is a completely ionized state. O2 dissociation is complete, N2 dissociation is complete. So you have charged particle from both of them. So that's a range of ionized gas. So a range of ionized state of the gas. So these are chemical reactions which will be important in all the temperature range that will be interested in such applications, particularly at very high Mach numbers. So 800, 2000, 4000, and 9000, by which 9000, yeah, by which the flow becomes partly or completely ionized and having charged particles. And this progress is this we have seen this table already. This progress is what relates to the chemical effects, and this is strongly coupled to the chemical effects. And what we have in this image is, I'll just quickly explain that part. This is we have already seen the flight velocity plots like this, flight altitude and velocity. So this is for a re-entry vehicle or a series of re-entry vehicles. The shaded region in between, the cross-hatched region in between, is for that corresponds to the shuttle, US shuttle, and in the space shuttle. And in that we can see that let's focus on any of these curves. So I'm just conveniently taking the middle one, that is the one which is corresponding one boundary of the space shuttle. What the plot shows is altitude versus velocity. The plot is altitude versus velocity, and the way the regions are marked is with respect to whichever temperature or high temperature phenomena are important in that. So at high altitude or high velocity, the resulting temperatures are going to be high, and that is where you are going to have nitrogen dissociation. And even beyond that, you will have ionization, but that is that's not coming in this flight corridor. So you have nitrogen dissociation, and as it comes down, you have the region of 2000 to 4000 where the oxygen dissociation is important. And then you have vibrational excitations, and only in a very low altitude region, relatively very low altitude region, you will have a the gas will be will correspond to a calorically perfect condition. So this is what happens when the during the re-entry phase and landing. The vehicle goes through a series of conditions where you have the importance of high temperature effects. And this is the nearby region we have discussed it earlier. You have a detached shock, you have a high temperature shock layer region, high temperature because it has undergone a normal shock, and the wall temperature is going to be high because there is a boundary layer, there is a flow deceleration, and there is transfer of heat from the flow to the wall. Okay, so this all mean that in hypersonic flows, in such applications, you need to account for reacting flows. So the moment we talk about reacting flows, the concept of chemical reactions and chemical equilibrium becomes important. So ever since air becomes chemically reacting, say maybe starting at 2000 Kelvin, the consideration of chemical reactions and the equilibrium state becomes important. What do we mean by chemical equilibrium? The chemical equilibrium, as you have studied right from the days of your high school chemistry or +2 chemistry, it's a state where we consider the reactions to be in balance. In balance in the sense you have forward reactions, you may have backward reactions, but there is they are all in a state of balance, so that there is no spontaneous change in chemical composition. So it doesn't mean that there are no chemical reactions. Actually, there are chemical reactions. Chemical reactions are there. Their rate is so high, but there is no. But they balance each other so that there is no change in the chemical composition. So that's what we mean by a state of chemical equilibrium. Whereas a non-equilibrium condition is like any state where you have a continuous spontaneous reaction. So the species keep changing, the species field keep changing as a function of time. So that's when we say that the gas is not in equilibrium, is not in chemical equilibrium. It could be either chemical equilibrium or thermal equilibrium. That is, there may be heat transfer, there may be regions of temperature gradient, there may be gradient, the presence of species gradient also. Species gradient leads to non-equilibrium condition. Thermal gradient leads to thermal non-equilibrium. Chemical non-equilibrium because of species gradient, and thermal non-equilibrium because of the temperature gradient. Now, usually in such analysis, reaction time is sort of considered as a parameter which can quantify the extent of equilibrium or the nature of the flow field. Equilibrium, when we say equilibrium, as I mentioned, you have chemical reactions happening, but the reaction is so high that you have the backward forward reactions sort of happening instantly, so that there is no net change. So which in turn means that the chemical reaction time, the time required for the completion of chemical reactions, is very high as compared to I'm sorry. The chemical reaction is the rate of reaction is very high, which means that the time required for chemical reaction is very low. So rate of chemical reaction is very high. Because of the high rate, the time that is required for chemical reaction is completion of chemical reaction is very low as compared to the flow time. What do you mean by flow time? Is the time that the fluid particles takes for translating from one place to another. So by the time the fluid moves from one location to the other, the chemical reaction has completed, and then you don't see any appreciable change in the measurable change in the composition. So in relation to the flow time, the chemical reaction time is small, or the other way around, the chemical reaction rate is very high, is infinite. So because as though the reactions are taking place instantaneously. So that kind of a situation is what is referred to as equilibrium. And the contrary to that, the opposite condition is non-equilibrium, where you have the composition keeps changing. Composition keeps changing because you have a species imbalance, and there is reactions, but the reactions are not fast enough to complete, which means that they keep occurring. So the flow keeps moving, reactions they keep taking place, and the composition keeps changing. So there are chemical reactions, there are collisions, but their rate or the frequency is not fast enough, or no, is not high enough to have completion of the reactions. So so what we actually mean here is that the chemical reaction time is high in non-equilibrium flows as compared to the flow time. So it's quite opposite to the equilibrium condition. Now, conceptually, when many of these studies in hypersonic flows, there is an intermediate concept of frozen equilibrium. That's unique. The analysis of that is unique to hypersonic flows, where the flow time is very low. That is, the flow velocity is very high. Now, here, frozen equilibrium is somewhere in between. That is, it's kind of an equilibrium, but the equilibrium is not established because of the high rate of reaction. It is actually considered to be in equilibrium because though there is imbalance, the reaction time is not high enough, or the collision, the intermolecular collisions is not high enough, is not frequent enough to have the reactions taking place. So what happens is the mixture composition is not changing. But then mixture composition is not changing, not because there is chemical reactions, or not because there is no species gradient. It's not changing because the chemical reactions don't have sufficient time to complete. So in non-equilibrium, you have composition changing because the reactions are taking place, though they are slow, they are taking place. But in frozen equilibrium, the mixture composition is not changing because the time there is not sufficient time to have intermolecular reaction to go to completion. And that kind of a situation is called frozen equilibrium. So frozen equilibrium indicates that it's not a real equilibrium, as we described or discussed earlier, where you have the flow or the reaction time being close to zero, or the rate of reaction is infinite. That's not the case here, but only it resembles equilibrium in the fact that the composition is not changing. But here the composition is not changing because the reaction rate is very slow, or the rate of reaction is very low, or the speed of reaction is very low. Okay, so so that's what is concluded in this last sentence. Though the mixture composition does not change, it does not mean that the equilibrium of the mixture is existing in terms of the temperature and pressure. It's not that kind of an equilibrium, but it's only because the reaction is too slow to take place. Okay, so an example of this is actually quite often this is used in rocket nozzles, etc., where you have a rapid expansion. So you can see that in many of the rocket nozzle studies, the flow is considered to be having a state of frozen equilibrium. Why? Because in that nozzle, as we know, in a CD nozzle, the flow is taking place. There is a continuous expansion. The static temperature is static pressure is coming down, and that's what as a result of the ensuing expansion. And remember that what comes through is a mixture of gases, right? Combustion gases. There will be there can be chemically reacting species, etc. But the flow is so fast that in the divergence section, the flow is so fast that there is no time for the particles to react. and also the pressure is dropping because it's an expansion process. So when the pressure is dropping, you have lesser molecular collision, intermolecular collision. So you may have lower rate of reaction. So all that can correspond to what we just mentioned as a state of frozen equilibrium. Okay, so coming to the context of hypersonic flows, usually the analysis is done. In fact, again, the extent of theoretical analysis is limited, but some of these concepts can be incorporated in the in numerical analysis and CFD modeling. Equilibrium as well as state of frozen equilibrium, etc., can be incorporated to CFD solutions, and this is how the chemical reactions, depending on the nature of the flow, the type of the flow, the Mach number range, etc., the chemical reactions are incorporated into the modeling of the flow or the theoretical calculations, so that the variations in temperature, or rather, the variations in composition because of reaction can be accounted for. Now, the one more related aspect of it, not related to high speed, high temperature, but usually applied or usually relevant in hypersonic flows, is the rarefication. In fact, some people consider or rather discuss this as a character of or along with the characteristics of hypersonic flows, which probably is not contextually so correct, because a rarefication, unless say high speed, high temperature flows, etc., rarification is not necessarily a feature, or is not because of the hypersonic nature of the flow. The importance of rarefied flows is many of the hypersonic applications involve low pressure atmosphere. Say as we know, re-entry space, where the high altitudes where the density is very low. A rarefied flow is one where the density is so low that your continuum concept will not hold anymore. Please remember that right from fluid mechanics, compressible flows, and even in this course, we always assumed continuum as granted. That is, we keep referring to Euler's equation, Navier-Stokes equations, etc., which are all based on continuum assumption. But then when up in the atmosphere, when the velocity, as we know, the density keeps falling, the continuum assumption breaks, and situations where the intermolecular distance is so high is what we refer to as so high that there is no exchange of momentum, etc., between the molecules necessarily. That kind of a situation is what we call as the rarefied gas, rarefied flows. So it is like the average distance that a molecule has to travel before it meets a neighboring molecule. Let's see what it means. Actually, in continuum flows, we assume that in fluids, the molecules are close enough so that if you apply a pressure on a pressure field on one place, it just communicated through the molecular interaction to the other parts. But then what if you have molecules so sparsely located? So it means that what a molecule experiences will not get communicated to another molecule, because the time or the distance that two molecules have to travel is too high to have a collision between them. So that kind of a situation where the molecular free path, the distance that a molecule travels before it meets another one, is too high to have frequent collision, is referred to as rarefied flow, or that what leads to that such kind of a situation is called rarefication. So in hypersonic flows, the importance of this is that since re-entry vehicles encounter hypersonic flows, and they also encounter correspondingly conditions of rarefied flow, where the continuum concept will not be allowed, will not be applicable. So that's a regime where what we call as the free molecule flow. Free molecule flow means the molecules are independent of each other. Now, this is quantified by, probably you would have heard of this Knudsen number. Knudsen number is a parameter that is used to say to determine whether the flow is ratified or not. And the definition is quite straightforward. It's lambda by L, where L you can consider it as maybe a diameter of the molecule, etc. Lambda is the mean free molecular path. L is a characteristic dimension. Lambda is the mean molecular path. So L is a characteristic dimension related to the flow field. Lambda is related to the molecule. So that is the mean free path of a molecule, which obviously is a function of temperature, etc. So usually when we consider continuum, the applicability of continuum, it is restricted to lower values of Knudsen number, that is Knudsen number less than 0.2. What does it mean? That is, if the mean free molecular path is relatively low as compared to the characteristic dimension, you can assume the flow to be obeying continuum. Which means that the molecule doesn't travel too much before it meets another one, which in turn means that they can interact, they can transfer energy, they can transfer momentum, heat, etc. So if that can happen because of molecular exchange, then we can consider that as a continuum flow. But then if it is too high, if the mean free path is too high, maybe because of low pressure or low density, actually low density, that is you have too less molecules within a given space, then the mean free path will be too high before it have any interaction, before a molecule meets another molecule. And that is at that condition, all the assumptions related to continuum will fail, and we cannot use the Euler's equation, etc. So hypersonic, we are just relating that to the hypersonic context. A hypersonic vehicle entering the atmosphere from the space, re-entry conditions will have to go through this low density effects also. So in certain areas, when we do the analysis, or when the hypersonic flow physics has to be taken into account to evaluate the aerodynamics, we will have to incorporate the low density effects also, which means that we cannot make use of Euler's equations, Euler's equation or Navier-Stokes equation for such analysis. Okay, so it just sort of the spectrum of Knudsen numbers that the re-entry vehicle analysis has to go through is quite high, quite large, that it includes the free molecular conditions also. Okay, so I just mentioned that in certain hypersonic applications, the rarification effects or the rarified flow effects also are important. Now we don't have to analyze it in this course, but then it's just I mentioned that ratification or the effects of ratification will be important in certain hypersonic applications. Again, it's not characteristic of hypersonic flow, but it's characteristic of some of the hypersonic applications like re-entry. So I guess with that, we can, you have any questions so far? If you don't have, then we'll just move on to the conclusion. We have sort of completed whatever is to be covered as part of this course. The basic aspects of hypersonic flows and the different analytical approaches, theories which are primarily inviscid, their formulations, the strengths of those theories and limitations, and we have seen how they are formulated, where we can apply them. Actually, wherever, though it is a theory course, actually, this is one aspect of this course. It's hypersonic flow theory. So, is the theory of hypersonic flows sort of dominates the syllabus and the nature of the course. But wherever it is applicable or wherever it is relevant, we have also considered specific applications of the theory where it can be, or it has been proven by experiments, or where it can be really applied in practice. We have seen those applications, we have considered them. We have also seen some of the instances where numerical calculations can be made use of, or useful estimates can be made using the hypersonic flow theory. So we have considered inviscid flow. We have seen how the fundamental aspects of viscosity are modeled, starting from the formulation of the boundary layer equations, and we have also seen how heat transfer is incorporated. Okay, so and then so these have sort of covered both the inviscid and viscous effects which are pertinent to hypersonic flow and its applications. And we have just discussed the effect of turbulence. So the theoretical models that we have seen so far are all restricted to laminar flow. We have seen the effect of turbulence or the conditions under which transition takes place to turbulence, and what are going to be the consequences of that. Okay. And wherever it is possible, I have made use of CFD. Because CFD being probably the only tool that we have here now, in which all the effects of turbulence can be incorporated. Effects of hypersonic flow in several practical applications can be incorporated. So what we have done as part of the later sessions of the course is to highlight some of the CFD results and use those results to explain things related to, say, boundary layer behavior, the temperature distribution within the boundary layer, the nature of thermal boundary layer, and how it relates to Prandtl number, etc. So the role of CFD in general, in at least in part of the hypersonic flow applications, have been also discussed through the results which are presented here. So this is all that I wanted to cover in this course, and I once again thank you all for your interest in the course. After you come here, if there are any topic or anything that we need to look again, or if there are questions to be clarified or anything needs to be looked at, I'll be more than happy to do that. So you can contact me anytime at your convenience when you come here. Looking forward to meet you all soon. Any questions, please? By the way, I have, as of now, I have uploaded all the PPTs, including what was covered yesterday. And today is also I'll upload soon. So that will complete all the PPTs uploading to the team. So and if you see that by mistake, if I have missed anything, please do let me know. I think I have uploaded all of them. Just in case I missed any, please let me know.
Sir,
yeah, please.
I have
please,
one
please.
small question.
Please.
Now, you said that hypersonic flow is generally considered only at rarefied atmospheres, right? At rarefied heights, right? So, if if it's not used in that case, then what would be the operational altitude if we're considering continuum hypothesis?
I just want to first, I'll come to what you asked, but then I just want to correct what you said, the first part of it. I guess you mentioned that hypersonic flow is considered only in rarefied. So that's not correct. Actually, many of the range of height, altitude where we have to consider hypersonic flow effects have rarefied effect. So it's not that hypersonic flow is restricted to rarefied applications. But then, sorry, second part, what did you ask actually? So in what height is it? What did you ask? Sorry.
Yeah, if not used at that altitudes, at which altitude under continuum hypothesis?
Okay, yeah. So if you are asking me from what altitude the rarification effects become important, probably
No,
that's
sir.
what you are
No,
right.
sir.
Yeah.
No. If
That
we are
that
using continuum hypothesis for hypersonic flow, in case we do that, then at what altitude will the aircraft have to travel maximum?
I
What
understand. Yeah, I understand that. Yeah. Say if you are talking about aircraft, that is for all everything applications that we deal with, like ramjets, scramjet, etc., and also for future advanced air breathing propulsion systems, all the altitude that people think of today, as of today, are all within continuum range. That is the density, the pressure, the temperature relation will have Knudsen number in the continuum range. So the altitudes that we have, you say usually, what should I say? Well within the limits of what you call as the inner space. So 50 kilometers and above that, etc. They are all the interesting. This one's for air breathing propulsion. So they are all within the continuum range. Now, if you are asking beyond that, up to what we can consider, that depends. I mean, we'll have to take the atmospheric properties, do a calculation. It's actually a straightforward calculation, though I myself have not done that. You can do the density, you can get the density of the atmosphere, you can calculate and correlate that to the mean through the temperature also, and calculate lambda, the free molecular path of for air, and then calculate it for a given configuration with a given L. So that's a important, that's importance, or actually that's a relevance of Knudsen number. That is, if I know a particular conditions at an altitude, I can relate that to the Knudsen number and see whether the condition is applicable. So if you're asking about aircraft applications, for whatever we know today, whatever the aerospace community is planning as of now, they are all within the continuum range. And beyond that, at any given altitude, we'll have to make use of the Knudsen number relation to find out whether rarefied effects are prominent at that altitude or not.
Okay, sir. Thank you.
I want to I told this a couple of times earlier, but I just want to remind you once again that for in some you need gas tables. So please do carry your E. Radhakrishnan compressible flow gas table, whatever gas tables. Please do take them when you come for exam. So you need them inside the exam hall. Just please be reminded to do that. Any other questions or anything that you want to ask? If not, we can stop now. I hope to see you all soon when all of you are back in the campus and comfortably settled back here. Okay, then once again, thanks a lot for the cooperation during the course. Sorry, somebody is trying to ask something? No. Yeah. Yes, I should not have forgotten that. I guess there is one team which has not presented yet, right? Team group number 4, the assignment. What? HFT. I'll just call the names. What did we complete all of them? Sorry. What did we talk yesterday? Can somebody please remind me? What did we say yesterday? I forgot. Is it that one team is remaining, or did we finish all?
Sir, I think
I'll check. We finished all. Sorry.
two groups presented.
Say that once again.
Class 2 groups presented. Sanjeev and I think Rashis.
Rashis, yeah. So they, sorry, Sanjeev, Rashi presented 1, 2. Group 5, Yuvraj. I think that yeah, they said they were presented. Yeah, great. Yeah, because I have marked it here. So that's why I think we are done with all. Okay then. Okay. Thanks again to all of you for the cooperation all through the course and your interest in that. Thanks, and bye. If you don't have anything else to comment, we'll.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.